Okay, so this last video is going to be, I think, relatively short. We'll see here how short we can make it. And this is going to be the last video that is going to wrap up our discussion on circuit biasing and active loads. So what that means is this is the last material that will be on the next exam. So for exam 3, this wraps up our material for exam 3. So normally I had the circuit drawn ahead of time, but I forgot to do that. So I could do here, I'll do this for the rest of it. I'll pause the recording. And magic, the circuit's done again. So obviously you can pause the video if you need to. Actually, I forgot the power supply here. If you need to do this. Now, the way we should go about doing this is doing the small signal model, which we'll go ahead and draw here. It's really easy. But remember here, what we're going to need to do here is we're going to need the output resistance for this, just like we did with the bipolar. Now, the good thing is that this is M2, this is M1, M out. That the output resistance here, I'll say RO2, is just 1 over, not 1 over, it's equal to little RO, the early voltage effect resistance. And so basically our small signal model is going to look like the following. And that's just a really ugly, rough sketch of it. But the reason I just did an ugly, rough sketch is that we should see this is going to be exactly the bipolar case that we had here, except we're dealing with MOSFETs. And so we're going to get here that my voltage gain is simply, and I'm going to emphasize that this GM is on the output MOSFET times RO and parallel with RL and parallel with RO2, which is the exact same equation that we got for bipolar. But we really shouldn't be surprised by that. And the reason we shouldn't be surprised by it is because, that's what we did when we were looking at it with all the resistors as well. Okay, so let's look at an example here to wrap this up here. So this example here, we're going to have lambda n equals lambda p, which is equal to 0.02 volts. Now remember, a lot of these examples that we've been going through and that are in your homework, they match all the parameters. But remember, don't assume that the parameters are going to be matched on an exam, because that's one way I can make the problem different and maybe slightly challenging. And I wouldn't say challenging, it's still just plug and chug. But to me, it makes sure that are you aware of exactly what you're doing, as opposed to, hey, everything's the same number, so we just plug the same number into every place. And so I'm writing down all of the parameters here. So this is what we're going to find here. Okay, so to find VIQ, let's look at the circuit here. VIQ is basically what does this DC voltage have to be in order for this to be biased. So really what VIQ is simply just VGS is all we're asked to find for part A. And so we're just going to go ahead and use the equation here that, well, we have ID is equal to Kn VGS minus VTN quantity squared. And so my current here is 0.4 milliamps. My Kn is 0.25 milliamps per volt squared. And then my VGS minus 1 quantity squared. And then I'm just going to do those computations. Again, I'm not going to show the work solving this. And when you do all the work to solve it, you get VGS is equal to 2.26 volts. And then part B is find the open circuit voltage gain. So we're going to need to know all the different values here. We're going to need to know what ROP is and RON. Now they're going to be the same, which those are going to be 1 over, and they're the same because everything again is matched, but don't just assume they're the same. Make sure that you use the correct parameters here. So this would be 1 over lambda n was 0.02 times my current is 0.4 milliamps. And when we do that, what do we get here? I don't think this video is going to be as short as I thought it was, but that's okay. We get 125 kilo ohms. So for part B, this would be, well, actually I forgot to compute one other thing. I need GM, which is just Kn times the square root of, alright, actually I'll just do this. I'll do 2 Kn VGS minus VTN. I mean, yes, there's several ways you can compute it, but that's one way. And so, because I already have what VGS is, so I have 1.16 times 0.25 times 2. And we get 0.58 milliamps per volt for GM is what we end up getting. And let me double check that computation here. I don't think that's right. Let me go back to the other equation that I'm used to using here, where GM is equal to 2 square root of Kn Iref, which would be 2 square root of 0.25 milliamps times 0.4 milliamps. And if we do that, what do we get here? 0.25 times 0.4 square root of that times 2, get 0.632 milliamps per volt. And then for the gain here, we would have that this is equal to negative 0.632 milliamp per volt times 125K in parallel with 125K. Which when we do that, we get 125 divided by 2 times we get that the gain is negative 39.5. And then for part C, what does our L need to be so that the gain is 1/2? Well, remember we have the gain equation up back here. That's negative GM RO parallel with RL parallel with RO2. So we actually have everything we need. So this gain now is negative GM times, well, actually let's just write the numbers down. So the gain that I'm looking for, it's 39.5 divided by 2. So this would be negative 19.75 has to equal negative 0.632 milliamps per volt times 125K and parallel with 125K and parallel with the load. And then we solved one like this with the bipolars in another video. It's the exact same. So let's just go ahead and do that. So we get 31.25 K has to equal 125K in parallel with 125K in parallel with RL. And remember the way we did this is we did 1 over 31.25K is equal to 1 over 125K plus 1 over 125K plus 1 over RL. And then we solved for RL. And let's go ahead and do that real quickly. And when you do that, you get RL is equal to 62.5 kilo ohms. Alright, so basically a standard length video here, but that's what we get here in order to get the gain to be 1/2. So we have, again, an open circuit gain formula and a loaded gain formula. Alright, so these formulas again will be provided, but I won't tell you the difference between them.